I would like to say that I had my privilege to collaborate with Gerard at least for 10 years, and I'm trying to follow his exceptional scientific style and also the professional ethics up to now. And both my co-authors, Yuri Engelbrecht and Mikhail Berezovski, is also influenced by Gerard. And the talk here is also has the foundation from the ideas from Gerard's works. So the talk about the inertial and thermal effects in the internal variable description of microstructure. What does it mean? First of all, I would like to start with motivation. As you know, the generalized continua like micromorphic, Cassirer second gradient, and so on, mostly have isothermal treatment, and microinertia usually introduced phenomenologically. At the same time, generalized thermoelasticity, classical at least, mostly interested in the hyperbolic heat conduction and almost consider rigid or homogeneous solids. But we expect that thermomechanics of solids with microstructure is a coupled theory with thermal and inertial effects. So I would like to say about the internal variable approach. So in internal variables we have the classical approach, so-called single internal variable theory, and this theory is limited usually by dissipative processes and parabolic evolution equations for internal variables. Recently we introduced the so-called dual internal variable theory, which provide the hyperbolic evolution equations for microinertia and microtemperature, and I would like to explain how it can be done. So I start with the Piola-Kirchhoff formulation of continuum mechanics. It is standard one, and I take this slide only for the notation. So this is Piola-Kirchhoff first stress tensor. This is full energy. This is kinetic energy plus internal energy. The capital S is entropy, bold S is entropy flux, and this entropy flux is not very classical. There is a so-called extra entropy flux, which in most cases may be zero, but it is not general requirement. So next we go to the material formulation of continuum mechanics, and main thing is the canonical balance of canonical momentum or material momentum, which is here. It is the linear momentum multiplied by deformation gradient, and the sign is for convenience only. Divergence of Eshelby stress, the Eshelby stress is here, and this is Lagrangian, L, capital L. And here in right-hand side, we have the so-called configurational forces. And they are three of them here. This is force of inhomogeneity. This is external configurational force, and as the internal, external, and the force of inhomogeneity, and they can be calculated if we know or specialize the free energy function. Then we have the balance of energy, and this is material heat flux, and as in previous case, we have something in the right-hand side, which is also can be calculated by if you know or specialize the free energy function. Clausius inequality is rewritten in these terms as follows. And now I go to the single internal variable theory. What is different from the standard theory, it is dependence of free energy function not only on the deformation gradient and temperature, and also of the some kind of internal variable, and for the weak non-locality we apply also the gradient of this internal variable. So then we can define equation of state. This is first Piola-Kirchhoff tensor, entropy, and this is some kind of internal forces. There is no real established names for that quantities. And material force and heat source, just in this case, are maybe divided in thermal part and intrinsic part in both cases. We apply the proposal of Gerard-Magen for the extra entropy flux in this form, and canonical balance laws slightly changes because we need to modify the Eshelby tensor, material heat flux, and also calculate these intrinsic forces and intrinsic heat source. But thermal source terms are calculated by temperature only. These modifications are the same. The heat flux has the additional term depending on the internal variables, and Eshelby tensor also has additional contribution, and intrinsic source terms depend only on the internal variables. So, dissipation inequality has this form. This is thermal part, this is intrinsic part, and to obtain the evolution equation for this internal variable, we apply standard assumption that this force here is proportional to the internal variable, time derivative of internal variable itself, and if this coefficient is positive, this quadratic form is positive, and evolution equation for internal variable can have the parabolic type of behavior, because this is only one time derivative here. Okay? So, we apply the dual internal variable theory by the extension of previous single internal variable theory. Why we need to do that, we will see later on. So we simply formally apply the extend the state space by the another internal variable and its gradient for weak non-locality. So we obtain additional forces or something like that. And entropy, and extra entropy flux is also modified by second internal variable. What is good for canonical balance laws, that's the shape of these laws not changes at all. Only the modification needed for the Eshelby stress and material heat flux, and this modification as previously is fully similar to the single internal variable theory. Okay? Even the intrinsic force also has the same shape for both contributions. Okay? So, why we need to introduce second internal variable? This is because evolution equations. In this case, the dissipation inequality has the same form, but intrinsic dissipation has additional contribution. And the solution of this inequality has a form of matrix. So this is, just now it is not so easy to imagine what kind of evolution equation we have. So I go to the example, very simple example, one-dimensional thermoelasticity, linear thermoelasticity, to show how it works. So again, I start with the some notation. So the balance of linear momentum in absence of body force, it looks like that. We have also energy balance. It is only for internal energy, and just now the entropy flux is denoted by J, not by capital S as in previous tensorial form. So we apply Hooke's law as usual. Entropy flux is classical, and the Fourier law is also usual, and all this results in the constitutive relation for one-dimensional linear elasticity in very usual form. This is mechanical part, thermal part, and coupled. So, if we can calculate the time derivative of internal energy, like that, and we know the definition of entropy, because it is the derivative of free energy with respect to temperature. So we go to the energy balance, and for the small deviations from the reference temperature, theta 0, we obtain the energy balance in this case, and these two equations fully determine one-dimensional linear elasticity without microstructure, of course. So, to include in the play the microstructure, we introduce first single variable theory, internal variable theory. Now this is more or less again the same story like previously, but just now we have scalars, not tensors. And the time derivative of internal energy is contributed by some terms depending on the internal variables. And we have energy balance and entropy imbalance, and eliminating this term, we obtain the dissipation inequality in this form. The main idea of the introduction of entropy flux by Gérard Magen is to eliminate this divergence term. So we go like in similar way and define the entropy flux like this. So it is standard entropy flux. This is some additional extra entropy flux. The Fourier law is generalized in this form, and we have intrinsic dissipation in this form. So evolution equation for internal variable follows from this dissipation inequality by the proportionality of this time derivative of our internal variables to this part. So we have quadratic expression which is always positive if coefficient is positive. Okay? So next, again, dual internal variable theory, again repeating. So we introduce the second one, introduce some additional terms. Again, we calculate the derivative of internal energy with some additional contribution, and obtain energy balance in this form, entropy imbalance as previously. Eliminating this, we obtain dissipation inequality. Again, we eliminate this divergence term in this way, determining entropy flux in more general shape. Thermal dissipation is achieved by generalization of Fourier law, and intrinsic dissipation take us the evolution equation for internal variable again in matrix form, and just now we start to analyze this. So this conductivity matrix, this one, can be usually decomposed in the symmetric and skew-symmetric parts, and if we apply the Onsagerian reciprocity, where these coefficients are the same, we maybe diagonalize this because it is 0, and in some appropriate basis, we can write the intrinsic dissipation inequality in this quadratic form, and it is also satisfied by non-negativity of eigenvalues R1 and R2. So evolution equations of internal variable completely independent, and in this case, internal variable, each of them can be described in terms of single internal variable theory, and we don't need to introduce any kind of second like I did in this case of Onsagerian reciprocity. But if we apply Canonical reciprocity, which is this one, we obtain the symmetric part and antisymmetric part, so it mostly contribute the dissipation, and this is not dissipative part like in generic. So in the pure non-dissipative part, capital R11 and 22 are 0, and we have the zero dissipation, and we obtain like something like that. We always have zero dissipation, and evolution equation for internal variables slightly different, because the duality means that first or primary internal variables governed by the second one, and vice versa, second one is governed by the first. So in this case, in non-dissipative case, we interpret these primary internal variables as microdeformation, and if we consider the partly dissipative case, when the conductivity matrix has some dissipation here and not dissipative part here, the evolution equation is different, and due to dissipation we can interpret the primary internal variable as microtemperature, which means the fluctuation of temperature above of the normal macro temperature. Okay? So now we have the to have the full story, we need to introduce dual internal variable for microdeformation and dual internal variable theory for temperature together. It is too much, but if we have this quadratic free energy, this is the standard part, classical part, this is for the first part for microdeformation, and this is for microtemperature. What is bad, it's only the number of coefficients, but nevertheless we can go and obtain evolution equation for internal variable in case of microdeformation. This is, you see, if we take the second time derivative of this, we have the first time derivative of this, and putting here this one, we obtained a hyperbolic evolution equation for microdeformation, and also we can define the microinertia. And in the second part, for the microtemperature, the evolution equation for internal variables is different, but still hyperbolic. But here we have also the first order time derivative additionally, and also we can determine the so-called thermal microinertia in some sense. Okay? And full system of equations for the thermoelasticity with internal variables, we have the balance of linear momentum where the terms of microdeformation and microtemperature exist. The balance of energy has additional term dependent only on microtemperature. Evolution equation for microdeformation depends on the displacement, and the evolution equation for microtemperature, microdeformation, here microtemperature, is also depend on the displacement. So all these equations are coupled with each other. So, and I would like to show you how it works, and this is very simple example. So we have some specimen, and we take some thermal pulse, Gaussian thermal pulse at this boundary, and we see what happened. So first I would like to show you how the classical theory working without any kind of internal variables. So it is very usual thing. So we have the temperature, which is slightly diffused close to the boundary, but because of the pulse, the thermoelastic wave is formed and propagates through this specimen. So you can see once more the formation. And microtemperature is 0, so it's no any kind of influence. And now I would like to show you what happened if we have microtemperature influence. It looks like that. So what we have? We have almost the same behavior close to the boundary. It is standard hyperbolic motion of macro temperature. We also have some kind of thermoelastic wave, but this thermoelastic wave generates some micro temperature difference, some contribution, and this micro temperature takes contribution to the macro temperature equation. So we have some kind of wave-like propagation of the temperature without hyperbolic equation for macro temperature. It's only the effect of microstructure. So it's probably almost all. And I would like to conclude that we can represent microdeformation and microtemperature as different internal variables in the full theory of thermoelasticity, and we have the hyperbolic equations for microdeformation and microtemperature. And these equations are consistent with the dissipation inequality. But for the macrotemperature, we have parabolic equations still. And the coupling between micro and macro motions provides wave-like temperature propagation. And without internal variables, it's still conventional thermoelasticity. Thank you very much for your kind attention.
Juris.
Yeah.
Questions?
You introduce microtemperature, but why not microentropy?
Okay, yeah, it's a good question, yes. It is probably more simple to introduce microtemperature, because if we introduce in your way micro entropy, you know the difficulties we immediately obtain. I will try. Now, probably I'm not start with the micro entropy. I start simply to see how the microstructure can be described in terms of internal variables. And suddenly we obtain something we can interpret like microtemperature. That's all.
So, Victor.
Yes, fluctuation from macro.
That is interesting. The idea when we have, let's say, shells means two-dimensional. In this case, physical and three-dimensional work. In this case, we have some homogeneous temperature. Some papers by Siemens and some other people, they introduce such so-called interpretation, microtemperature.
Why not?
This, then they are some manipulation, dynamical, they also should introduce some different, the same parabolic equation for this second temperature.
It is good. It is good remark. I need to take more attention for that. It's okay. Okay.
If I understood well, this formula can be applied to any current depending on variable and depending on its nature.
Yes, you're right.
Take some relation or another thing, no? But then should we ask for several objectivity, should we define objectivity each time depending on the nature of the variable?
Yes.
Will influence the equations and also the
Yes, we were very careful and publish. Probably it's not appear, but it is accepted for the publication in the continuum mechanics and thermodynamics. This is thermodynamic theory of the microstructure, and there is no such kind of application. This is fully thermodynamic theory with objectivity and so on. And I have no just now time to explain all these things. It is taken into account.